I am Basir-Ahamed-Khan, Assistant Professor of Department of Physics, Krishnath College. This is lecture 2 of module 6. In my previous lecture, I already told about the introduction of special theory of relativity. In my previous lecture, I told about some topics on what is the inertial frame of reference, what is the fundamental postulates of special theory of relativity, Lorentz transformation, relativity of simultaneity, order of events, and length contraction. Now, today I will discuss about these topics: time dilation, relativistic addition of velocities, and variation of mass with velocity. First of all, the time dilation. The time dilation, let us consider two inertial frame S and S dash. S dash S is the x coordinate, y coordinate, x y z, and S dash frame x dash y dash z dash. The S dash frame is moving with a uniform velocity v along positive x direction with respect to S frame. Now, to deduce the time dilation between two different inertial frames, we consider two events occur at a point x dash in S dash frame. At time t1 dash and t2 dash, as noted by a clock carried by S dash frame, then the time interval between the two events is t0 equal to t2 prime minus t1 prime. I repeat again, S dash frame is moving with a velocity v with respect along the positive x direction with respect to S frame. Now we consider two events in S dash frame occurring at a point S dash at time t1 dash and t2 dash. Therefore, to an observer who is staying in S dash frame, the measurable time of these two events is equal to t0 equal to t2 prime minus t1 prime. This is the proper time. Now, if an observer who is staying in the S frame measured the time of these same two events from S frame, then with respect to him the time of these two events equal to, this will be not t0, it will be t. That means the relativistic time measured by an observer in S frame equal to t2 minus t1. This is equation 1 and this is equation 2. Now, using the inverse Lorentz transformation equation, we get t equal to t2 minus t1. The value of t2 equal to t2 prime plus vx prime by x square divided by root over of 1 minus v square by c square, and t1 equal to this t1 prime plus vx prime by c square divided by 1 minus v square by c square. That means t2 prime minus t1 prime divided by 1 minus b square by c square. This equal to t0. Therefore t becomes t0 divided by root over of 1 minus b square by c square. So this is the expression of t and t0. t0 is the proper length which is measured by an observer in s dash frame, and t is the time measured by an observer who is staying in the s frame. Therefore the relation between t and t0 becomes t equal to t0 root over of 1 minus divided by root over of 1 minus v square by c square. Now since v less than c, therefore root over of 1 minus v square by c square equal to less than 1. So from this relation we can say that t greater than t0. That means t is greater than t0. Thus the time interval between the two events occurs in s dash frame appears to be longer or dilated to an observer in s frame. I repeat again, thus the time interval between the two events occurs in s dash frame appears to be longer or dilated to an observer in s frame because t greater than t0. That means thus to an s observer all events in s dash appears to occur slowly, that is a clock in s dash runs slow. Now the second topic is relativistic composition of velocities. Relativistic composition of velocities. Again I consider two frame s and s dash. S frame means S frame is x, y, z, and S dash frame equal to x dash, y dash, z dash. S dash frame is moving with a positive velocity v along positive x direction, and I consider a particle move along x direction with velocity u prime with respect to s dash frame. Therefore we can say that u dash equal to I u x prime plus j u y prime plus k u z prime. Let a particle is moving with a velocity u dash prime, moving with a velocity u dash relative to s dash frame, then we can write u dash vector equal to I u x prime plus j u y prime plus k u z prime. We want to determine the velocity u of the particle with respect to s frame. The particle is moving with velocity u prime with respect to s dash frame. We want to calculate the velocity of the particle with respect to s frame. This is our aim. So the velocity u of the particle with respect to s frame equal to I u x plus j u y plus k u z. U x dash u y dash u z dash are the components of velocity components of the particle with respect to s dash frame, and ux, uy, uz are respectively the velocity component of the particle with respect to s frame, with respect to s frame. We have then we have ux, we have ux dash equal to dx dash by dt, uy dash equal to del y dash dt, and uz dash equal to del z dash by dt dash. This will be dt dash. Okay, there, and ux equal to dx dt, uy equal to dy dt, and uz equal to dz dt. Now the Lorentz inverse transformation are Lorentz inverse transformation are Lorentz inverse transformation are x equal to nu, x equal to nu x dash plus vt dash, y equal to y dash, z equal to z dash, t equal to nu prime t dash plus vx dash by c square, where nu equal to 1 by root over of 1 minus v square by c square. Therefore dx equal to nu dx dot plus v dt dot, dy equal to dy dot, dy equal to dy dash, dz equal to dz dash, and dt equal to nu dt dash plus vx dx by c square. Therefore, from this equation we can write thus ux equal to dx dt, that is the value of dx, I put the value of dx equal to nu dx dash plus vt dash, and value of dt equal to nu dt dash plus vx dash by c square, that is dx dash by dt dash plus v divided by 1 plus v dx dot dash dt dash divided by c square. That means ux equal to ux dash plus v divided by 1 plus v u x dash divided by c square. This is the value of ux. This equation gives the value of ux means the velocity component of the particle along x-axis with respect to s frame equal to ux dash plus v divided by 1 plus v ux dash by c square. This is equation 1. uy, then what is uy? Uy equal to dy dt equal to dy dash divided by nu times dt dash plus vx dash by c square equal to dy dash by dt dash divided by nu 1 plus v dx dash by dt dash divided by c square equal to uy dash divided by nu 1 plus v ux dash divided by c square. This is equation 2, and uz equal to dz dt equal to dz dash divided by nu dt dash plus vx dash by c square equal to dz dash divided by dt dash and nu 1 plus v dx dash by dt dash by c square. That means uz dash divided by nu 1 plus v ux dash by c square. This is equation 3. So we get the velocity component of the particle with respect to s frame. Therefore equation 1, 2 and 3 are the velocity component as the composition of velocities. Now special case 1. When the particle moves along x-axis, that is particle moves along x-axis, particle moves along x-axis, that is ux dash equal to u dash uy dash equal to 0 and uz dash equal to 0. Uy dash equal to uz dash equal to 0. Therefore, we get ux equal to from equation 1 ux equal to u dash plus v divided by 1 plus u dash v by c square. From equation 1 we get u dash plus v divided by 1 plus u dash v divided by c square. Uy equal to 0 as uy dash equal to 0 from equation 2 and uz equal to 0. Thus with respect to S frame, thus with respect to S frame, the velocity of the particle is velocity of the particle is u equal to ux equal to u dash plus v divided by 1 plus u dash v by c square. When the particle is moving along x-axis, this is known as law of addition of relativistic velocities. This is known as law of addition of relativistic velocities. Velocities or velocity addition theorem velocity addition theorem if now if u dash and v is very small compared to c, then this equation becomes u equal to u dash plus v, because we neglect the term u dash v by c square is very small, very small. When very small, that means if u dash and v are very small compared to c, then the quantity u dash v by c square is very small, and I neglect this and I get from this above equation u equal to u dash plus v, which is similar to the classical relative velocity of relative motion, which is the classical relation for relative velocities. Now case 2. This is 1, this is case 2. When u dash equal to c, then u equal to c plus v divided by 1 plus c into v by c square. it will become c 1 plus v by c divided by c into 1 plus v by c, 1 plus v by c equal to c. This is very interesting. Thus, if the particle in S dash moves with velocity c or velocity of light, then its velocity with respect to s is also c. Thus, if a particle, thus if a particle in if a particle in S dash move with velocity of light with velocity of light c, then its velocity with respect to s, its velocity with respect to s, with respect to s is also c, Case 3. Case 3. Case 3. When u dash equal to c and v equal to c. When u dash equal to c and v equal to c. v is the velocity of 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 s dash frame with respect to s. That means when the particle is moves with the third case is when the particle is moves with velocity v, velocity c, and also s dash frame is moving with velocity c with respect to s, then from velocity addition theorem we get u equal to c plus c divided by 1 plus c dot c by c square equal to c. Thus the addition of any velocity to c nearly reproduced to c. Thus the addition of any velocity to c reproduced to c we get these things here and here. With these two relation we conclude that the addition of any velocity to c will is reproduced to c. Hence we conclude that the velocity of light is the highest velocity or limit of attainable in nature, upper limit of attainable in nature. That means we say that we conclude that the velocity of light is the maximum or upper is the upper limit is the upper limit of velocity attainable in nature. Velocity attainable in nature. Attainable in nature. Attainable in nature is the highest velocity or the max upper limit of velocity attainable in nature. Now the last topic. Now here is a problem. There is a problem. So that the resultant the resultant of two velocities so that the resultant of two velocities is being less than c less than c is also less than c is also less than c that means the two velocity from the addition of velocity addition theorem, we have to show the two velocities which is less than c. After the addition it becomes also less than c. Therefore let velocity u dash equal to c minus p and v equal to c minus q, where p and q greater than 0. Therefore from velocity addition theorem, u equal to u dash plus v divided by 1 plus u dash v by c square becomes c minus p plus c minus q divided by 1 plus c minus p into c minus q divided by c square equal to 2c minus p plus q divided by c square plus c square minus c p plus q plus pq divided by c square equal to c times 2c minus p plus q divided by 2c minus p plus q plus pq by c. Since pq greater than 0, since p and q greater than 0, therefore pq by c greater than 0 and the denominator is less than the the denominator is less than the numerator. Therefore, u 2c minus p plus q, this is denominator is greater than the numerator. That means here 2c minus p plus q plus pq by c. So from this we say that u less than c. That means the resultant velocity of two velocities which is less than c is also less than c. This is proved. This is proved. Now the last topic, velocity mass variation of mass with velocity. Variation of mass with velocities. Variation of mass with velocities. Variation of mass with velocity. Here I without proving this relation mass and velocity, I just finally I just write here the mass is the apparent mass and m0 is the actual mass then, and v is the velocity of the particle of the mass, then becomes m equal to m0 root over of 1 minus v square by c square. In my class lecture I deduce this relation, but in the video lecture I just put here the final result of variation of mass with velocity, where m is the apparent mass when the velocity of the particle is v. Apparent mass when the particle moves with velocity v, and m0 is the rest mass, actual mass or rest mass, actual mass or rest mass. Then the relation between m and m0 equal to m0 root over of 1 minus v square by c square. Again, since v less than c, root over of 1 minus v square by c square less than c, that is m greater than m0. Thus we conclude that from this relation the mass apparent mass, or when the particle moves with velocity, at that time the mass of the particle is always greater than the rest mass of this particle. And if I plot this, the mass with velocity, then if I plot, this is velocity v, this is particle mass, then I will get this type of this type of this type of curve, which is this type of, this is c, this is 0, this is m0, this is rest mass, and this is mass. This figure represents the mass is increases with the increase of velocity of the particle. And when the velocity of the particle is c, that means when the velocity here, when the velocity of the particle is c, v equal to c, then if v equal to c, then m equal to infinity, then m equal to infinity. From here I also show, this graph also show that when velocity v equal to c, the mass becomes infinite.